All right, seems to be working. Let's hope for the best, and let's get going. So, I will start with number one. Right. So list the two key properties of a Dirac kernel that make K into a Dirac kernel. Both having to do with integrals, and so there one is that. Oh my! Let's try that again. Okay, there we go. The integral over the interval, which because everything's centered around zero, we generally write for a Dirac kernel as being being from -1/2 to +1/2, but it's still the circle. So this is so this says that the total is total integral is 1, which with the fact that which you actually can think about if you combine it with the fact that Kn is non-negative, that actually means that the first two things are really just saying that Kn is a probability distribution. I think I said that in class, but I'm sure it's in the recording somewhere. Anyways, so the first two properties are really saying that that Kn is a probability distribution, and then the last property is the interesting one. It's that well, let me draw the picture first. I'm stalling so I can remember. The picture is that as here's 0, as n goes to infinity, then Kn will be concentrated at 0, which means, and then the formal way of stating that is for every delta. So that's one property, and the other property is that for every delta greater than 0, oops. Actually, this is star. This is also star, and for every delta strictly between 0 and 1/2, be like really fussy about this. The limit as n goes to infinity of the part of the integral that's outside of a delta neighborhood of here's minus delta plus delta. So it's the part of the integral of K with respect to x, that is outside that interval. In other words, that where x is the absolute value of x is greater than or equal to delta, goes to 0. So that's yeah. So again, that's just saying that the stuff outside. It's here. There. I'll type something. So that says i.e. the portion of the integral outside a delta neighborhood of 0 goes to 0 as n goes to infinity. Okay, so there we go. There's part 1. Number 1 is number 1 okay? Yeah. So please, hey YouTube, please say yes on it. You're representing the whole class, so please say yes if and only if number 1 is okay. Does the limit on the inside? Well, that's a good question. So remember, the total integral is going to be 1. So so the portion inside the integral, sorry, the portion inside the delta neighborhood goes to 1. And it's 1 and not like infinity or something, because you want to think of it's representing a percentage. Wow, that was ugly, but I think that worked. Oh my goodness, my computer is so slow. Yeah. So when I say that Kn represents a represents a probability distribution. It sort of it sort of gives you percentages. So the total area under the integral between two parts of the interval represents the a percentage of stuff in that interval. And so yeah, so if the percentage outside the delta neighborhood goes to 0, that means that the percentage inside the delta neighborhood goes to 100%, which is 1. So make sense? Okay, so now on to number 2. All right, so true falses, true false explain, as always. So true false, suppose H is continuous and Kn is a Dirac kernel, then true or false, it must be the case that the convolution of H and Kn converges uniformly to H on S1 and goes to infinity. True. This is, in fact, the main new result of section 8.4. Right. So in order, or at least the sort of or at least tool. Right. So the first thing that's proven in section 8.4, the hard part of 8.4 is to prove exactly this theorem that if you have a convolution of the Dirac kernel, you take the limit as n goes to infinity, that converges uniformly to the original function as long as the original function is continuous. And then we sort of use that tool to prove all the stuff that we need that we've been wanting to prove about Fourier series. But yeah, so that's the main point. One of the main points of 8.4. So is number 2 okay? Okay. Next, number 3. True or false? It is possible that there exists some F in L2 and some for full. So yeah, so that's a good question. So for full credit, would citing 8.4 suffice, or would we need to expand? Well, for full credit, you just need to write true. Remember, you don't have to explain true answers. And the honest truth, if I know the answer is true and I read true, I just go check, and I don't actually read anything. I don't read anything that comes afterwards. So remember, it's a reasonable strategic thing to know is that well, I don't know. It's probably not worth gaming it out, but just so you know, as long as if the correct answer is true, and you write true, it doesn't matter what else you write. Okay, so true or false? It is possible there exists some F in L2 and some complex numbers C-5 through C+5, such that the distance between F and F5 equals 2, and the distance between F and this other trigonometric polynomial is equal to 1. So, and that answer is false. F5 is the best possible approximation to F among trigonometric polynomials of degree 5. So this thing over here, which is a trigonometric polynomial of degree 5, can't be better. And you don't have to cite this by name. You just need to know the fact that F5 is the best possible approximation among 2F among trig polynomials of degree 5. But just for reference, this is the best approximation theorem. Yeah. Right, from 7.4. Okay, so that's a little oops. Sorry. Hang on a sec. Yeah, that's okay. All right, so sorry. That was that strange intrusion was Zoom. Say, I think did you actually see that weird little box that showed up? Or did only I see that? Yeah, okay. So that weird little box was my computer telling me that the recording in the previous exam run through that I just did is now ready to be saved, and so there we go. Sorry about the weird little box. Anyway, so Stacey, you asked, it would be 0, not 1. What would be 0, not 1? Oh, I think I know what you mean. You're saying this, that should be at least 2. Right? Because this let me get the tool here. So this thing here, that represents the error in the sort of size of the error in the approximation between f and f5. And this represents the size of the error in the approximation between f and whatever this is. And so the best approximation theorem says that this is as good as it gets if your approximator is a polynomial, is a trig polynomial of degree 5. And so there's no way that this can be better, because error of 1 is better than an error of 2. So that makes sense?
Yes. Is that not F5 though? What is the summation called again?
Is that not? I'm sorry, I didn't quite catch the first word. Is that not?
What is F5? Like the
Oh, F5.
summation.
Oh, right. So
Summation.
F5. Yeah, let me remind you what F5 is. F5, remember, it is a sum from -5 to +5 of something times E sub n,
Oh.
but it's F hat of n. But there the coefficients are the Fourier coefficients. Yeah, F hat of n.
Okay.
Yeah,
And
so
the CNEN is just
something else. It's some other random approximation.
okay.
So yeah, so again, the best approximation theorem says that a random approximation cannot possibly be better than the Fourier approximation. Okay. So yeah, well, yeah, that one takes a little thinking to make that make sense. Okay. Next, so true or false? Is it possible there exists some continuous function f on on S1 such that the sum of the squares of the coefficients of f hat of n equals 7, but the integral of the integral of f squared equals 8. Well, that's false. It's got to be false, right? Because there's 7 and 8. How could it be? Well, but okay, why is that? Um, so so the isomorphism theorem for Hilbert spaces says that that there's 2 different ways of computing this is like that summation thing we did in class where we computed the norm squared of f in 2 different ways. One is by definition, and the definition of the squared norm is it's the integral of the square of f from 0 to 1. And the other way of computing the norm squared of f is by theorem. So that part is by definition. or less. And the interesting thing about the isomorphism, one of the interesting things the isomorphism theorem says is that this other side is by theorem is that the norm of f squared is going to be equal to the sum of the sum of the squares of the Fourier coefficients. That's by theorem. And yeah, and I'm there's a person's name. It's and I can never remember the person's name. It's like some French dude name begins with P. Plancherel. I don't know. French guy whose name begins with P. One of them. And it doesn't help that there are two of them, and they both have very similar looking facts. Anyway, whatever. By French guy's theorem, those things must be equal, and so and you can't have 7 equals 8. Okay, so that's it for the true false. Any remaining questions about the true false? And I'm going to wait till our brave volunteers for being here say yes. These are all 3 true false. Okay. Oh, hey, we have another brave volunteer. Okay. There we go. Moving on. All right. So let V let V be an inner product space and let T be a function from V to itself, such that T is linear or such that this stuff is here. And let Fn be sequences in V, which somehow, for some reason, I decided to make myself not sound like Gollum there. So let Fn be a sequence in V. State the sequential definition of what it means for T to be continuous on V. So A, if the limit as n goes to infinity of Fn equals F, then so remember, sequential continuity says that if the limit of the input converges to F, then the limit of the output goes to T of F. The limit of as n goes to infinity of T of Fn equals T of F. Or i.e. T of the limit of something as n goes to infinity equals the limit as n goes to infinity of T of something. You can pull limits inside and outside of T. So remember that was something we talked about for the definition of the sequential definition of continuity for ordinary functions, and the same kind of thing here works for functions on with more complicated inputs and outputs. Continuity means you can switch limits and you can push a limit inside a function. So B, define this. The sum as n goes from 1 to infinity of f sub n as the limit of finite sums. Well, remember this is equal to the limit as n goes to infinity of the sum as little n goes from 1 to capital N, of f sub n, except I have a lowercase n here where I should have a capital N. This is incorrect. And now I should go to capital N. Right. Sorry. So the infinite sums are the limits of the finite partial sums. So I hope that looks familiar from chapter 4. And I guess in chapter 4 they were series of numbers as opposed to series of like vectors, basically, or a series of functions, but it's the same definition. Now suppose T is continuous on V and the sum and the sum as n goes from 1 to infinity of Fn converges in V. Prove that this is well, basically evaluate this thing. Okay, so part C, T of that infinite sum, and this is sort of now by definition, this is T. So I'm gonna kind of do this like, do this like a sort of 2-column proof. Like every time I do something, I'm gonna give a justification for why it works. So this is essentially that's the definition. That's the definition of an infinite sum, but I'll just say by part B. And now I can now pull out that limit. F sub n. And that's by part A and continuity. The fact that T is continuous. Right, that's what part A says. Part A says you can switch. If you have a limit inside T, you can pull it out. And that's equal to, I'm going to run out of space. The limit as n, capital N goes to infinity of the sum as little n goes from 1 to capital N of T of F sub n. And that holds because T is linear. T is linear. Right, which is one of the assumptions. You have to assume linearity to make that work. And now, and this will now be equal to the sum as little n goes from 1 to infinity of T of F sub n. Again, that's by, I guess that's by B, or by definition of an infinite sum. All right, so I feel like they took a lot of space, but really, it's really not that deep, in the end. So there's 5 in its full glory where you can see everything. So any questions about 5? Is number 5 okay? Oh, Ursun, he said, why do we suppose convergence of that sum in C? Which sum? You go ahead and open up your mic. Oh, the infinite sum of the Fn. That's given. Fn converges in V.
Yeah, sorry. I'm just curious why why is that given? Does it affect the proof at all?
Yeah, I mean, if that doesn't converge, well, I mean, you can't really state then the statement doesn't make any sense. That's a good question. You would have to be more careful about what you said. That is a good question. So for example, if that didn't converge, there wouldn't be an actual input value to input into T in the first place. So yeah, you need the convergence of that sum in order to be able to ask the question, let alone prove the answer. Okay. Any other questions? Everybody else is 5 okay? Say okay. Say yes. Okay. Now back to width. All right. So let F be continuous, and recall that, well, that's what E sub n of x is. Use the definition of convolution to prove that thing. Okay. So, well, we're going to start off by writing out the definition of convolution. So it's the integral from 0 to 1. It's the integral over the circle of E sub n. Oh gosh, it's E sub n of something, that's something complicated, times F of something less complicated with respect to T. And remember, so the integral. So the thing to remember is that the things to remember the definition of convolution are that there's going to be a bunch of T's in here, because it's an integral with respect to t. But then also the point is the sum, whatever these arguments are that you put in here, their sum has got to be x. The sum of these things, I always have to go through this to remember the definition of convolution. The sum is the what you might call the outside variable, the variable that's sort of left over after you've done the integral, the outside variable x. Okay, so that yeah, that's so just so you know, that's how I remember the definition of convolution, is that the sum has to be x. Okay, so now this is the integral from 0 to 1 of e to the 2 pi I n x minus t f of t dt. And so this is equal to the integral from 0 to 1 of e to the 2 pi I n x times e to the minus 2 pi I n t f of t. Okay, that's actually probably the main substance of what's going on, is to remember the definition of convolution and then do that one little move. But are there any questions before I finish up? So just real quick. Any quick questions before I go ahead and finish this up? Okay, well, because x is a constant with respect to the integration, I can pull it out. So this is e to the 2 pi I n x times the integral from 0 to 1 of f of t times e to the 2 pi I n t barred, because it's just the bar, because taking the bar of e to something puts the bar on the exponent, and when you bar that, you just get it's negative because it's purely imaginary. Or in other words, this is equal to e to the 2. This is equal to, sorry, e sub n of x times the integral from 0 to 1 of f of t times e sub n of t bar dt, and which, remember, by definition is f hat of n. That one wasn't so bad. So any questions about number 6? William, I'm going to assume that no means there are no questions. That's supposed to, this is not okay. So let me know if it's not okay. Yeah, it's okay. Okay. Yeah, no questions. That's reasonable. That is a very, okay, we have 7 and 8. Here we go. Okay. So state the Hilbert space absolute convergence theorem for that thing. So so remember, L2 of S1 is a Hilbert space. That's the important thing. That thing converges as an element of the Hilbert space. Oops. In L2 of S1, if and only if the sum of the squared Fourier coefficients, squared absolute values of the Fourier coefficients, converges as a real number. Okay, now suppose that for all integers, basically a sub n is less than or equal to, well, there's some junk in there, but it's basically 1 over the absolute value of n. And we want to prove that we want to prove that that series we want to prove that this series converges in the Hilbert space L2 of S1. Okay, and so we're going to use the comparison theorem. I'm going to try to be out of having good habits. I'm going to try to do a careful version of the comparison theorem. And the point is, so eventually we're going to want to understand the convergence of that series of numbers. And so the place we will start is by comparing each term with something more manageable. Which I don't know is less than or equal to yeah, well, anyway, oh yeah, it's less than or equal to 7 over n squared for n not equal to 0, which we can ignore, right? Right, because if you make the denominator smaller, that means you make the whole thing bigger. Great. Yeah, this is one of the, we haven't done that so much of that in 131b, but remember back in 131a, or even just sort of Calc 2, you have to think, oh God, I'm doing comparison, and by making the denominator smaller, I make the whole thing bigger. Yeah, there's a lot of that in 131a. Anyway, okay, so we know that if we ignore n equals 0, then that series converges. That's a p-series test. By the p-series test, with p equals 2, is bigger than, strictly greater than 1. So the sum, since we only change finitely many terms, those finitely many terms don't matter, and so the sum as over all integers little n of the absolute value of a sub n squared converges by comparison. Oops. Comparison. And therefore, and that implies, I mean, it's equivalent to, but in particular implies that the sum that we were really interested in, the sum of a and en, converges in L2 of S1 by the Hilbert space absolute convergence theorem. Yeah, there we go. So there's that. There's part B. In its full glory. So now is number 7 okay? William, everything okay? Okay. One more to go. All right, so let k be a non-negative continuous function such that blah, and I hope everybody recognizes, okay, well, this is like some sort of, it's, k is something like a kernel. All right, so you should think like, oh, this is like all that stuff we had to do in problem set 9 about kernels. So this is hopefully, what I really try to do is I try to make every problem on the exam based on some homework problem, and you hopefully you remember like, oh, this is like those kernel estimates. Okay, so define what it means for f to be uniformly continuous. It means that for every epsilon greater than 0, there exists some delta depending on epsilon, but only on epsilon, greater than 0, such that for all x and y in S1, if the distance between x and y is less than delta of epsilon, then the distance between f of x and f of y will be strictly less than epsilon. Okay, so that's the meaning of uniform continuity. Comma. There we go. All right, so that's uniform continuity. So how many points would you earn with partial credit? I don't remember. You know, I think part A was only like, it's usually part A is, say part A is like 3 points. You might get like 1 point for partial credit or without uniformly, or maybe 2 points. I don't know. You know, less. But these when I have this thing where I have the definition, there's a preface to the proof. The definition really isn't worth that much by itself. That's really meant to be a hint. So like, hey, now you're going to use this definition of uniform continuity. Oh, and there's there is a missing there's a missing assumption. Whoops, my bad. Well, good thing we did this. So this is to be assumed. We're going to assume this in part B. Otherwise, part B doesn't make a whole lot of sense. So we're going to assume that f is uniformly continuous. So just be extra careful. Let me call this delta 1 because this is a I guess I'll call this epsilon 1. Yeah, because the deltas and epsilons in A might be different than deltas and epsilons in B. So right. So prove for every epsilon greater than 0. That means assume epsilon is greater than 0. There exists some delta greater than 0. So I'm going to let delta be something. I don't know what. Such that for any x with the absolute value of x less than delta. Okay, so for any x, so assume now that the absolute value of x is less than delta, and eventually you want to conclude, oh goodness, eventually we matchingly want to conclude that the integral from 0 to 1 of the absolute value of the integral from 0 to 1 of f of x plus t minus f of t times k of t dt is less than epsilon. Okay, so there we have it. Yeah, there we go. And I guess I'll stall for time. This really is given as t plus x. I guess that's actually helpful. So we start. So when we do this proof, we're going to start off by looking at this integral estimate of f of t plus x minus f of t. I don't think I left enough space here, but okay. Well, that's life. I'll figure something out. K of t dt. Well, okay. So whenever you see whenever you're trying to bound an absolute value of an integral, really the worst, you might as well push the absolute value inside, because the worst possible case is going to be when everything's positive anyway. So you might as well assume that you might as well push the thing inside, because k of t dt, because that's the worst case scenario anyway. All right. And so now, what do we know? We know that the integral, if we could just get rid of the other stuff, that's going to give us 1. So, I mean, the integral of all this other stuff is going to give us 1. And so I get, right. And so we want, yeah, well, I guess I'm a little nervous about this sort of thing, so I'm gonna do overkill. So I know that somehow I know that if I replace this with an epsilon over 2, I don't have to think about it. I just put it less than or equal to, that's fine. Which is going to be equal to epsilon over 2 time is going to be a constant. So let me sort of say, even though this won't be in the final answer, this is the sort of thing that we hope. Well, okay, I'll erase that later. So, but yeah, we hope that this is going to happen. We hope that we're going to be able to replace the difference between the distance between f of t plus x and f of t with some small number epsilon over 2, because that's kind of our only hope for proceeding. I don't know how else we could possibly get to having this all be less than epsilon. But once we do that, this is equal to epsilon over 2 times the integral of k over t, and since k over t is non-negative, and that's equal to epsilon over 2, which is in fact less than epsilon. So if we can somehow get this to work out, if we can be sure that f of t plus x minus f of t is going to be strictly less than epsilon over 2, then we're going to be good to go. So that's what we want. So I guess I didn't quite leave enough room here, so I'm going to sort of start writing this down. So the fact that we're going to need is that f of t plus x minus f of t will be less than epsilon over 2, and we're going to justify that in a minute. But okay, before I go ahead and do that, is everybody sort of good? Is everyone good so far? But with sort of like, why, sort of the process, like, well, we sort of hope that particular quantity will be small, because and indeed, if that particular quantity is small, then we can go ahead and get to the end and show that the integral we want is less than epsilon. So yeah. Anyways, is everybody okay with the fact that it all comes down to proving the inequality in green? Oh, I use delta of epsilon. Just my handwriting is terrible. Sorry. Sorry, Stacy. Let me go fix that. Yes, this should be delta of epsilon 1. Okay, so I think I hope you eventually see that what the delta we want is delta of epsilon over 2. So what we're sort of doing here, we're letting epsilon 1 or delta 1 of epsilon over 2. So epsilon 1 is going to be epsilon over 2. So we're applying the previous epsilon delta pair, but with epsilon over 2, the new epsilon over 2 instead of the old epsilon 1. So because if delta, well, that wasn't good. My computer does this sometimes. I need a new computer. So if delta is equal to delta 1 of epsilon over 2, then that means that if I use y and z here, if the distance between y and z is less than delta, then the distance between f of y and f of z is less than epsilon over 2. Dang it. Okay, it's refusing to let me write over there. Is less than epsilon over 2. Right, so that's the property that we get by choosing that particular delta. All right, and here why is it that the absolute value, the distance between f of t plus x and f of t is less than epsilon over 2? That's because the distance between t plus x, t plus x and t is equal to x, the absolute value of x is less than delta. Right? If again, if this distance is less than delta, then this distance is going to be less than epsilon, and then we're good. So I guess we don't need to rely on hope anymore. Hope is not a plan, but it is true that these two things, we are able to replace the one thing with the other because of this observation over here. And in fact, I hope you remember at some point that I think that I can't, either we did this in class, I think it was probably both. Either we did this in class or in the homework, but remember exactly this thing where you have t plus x minus t, and then that's equal to the absolute value of x, which is less than delta. Either that was either on the homework or that you had to use that at some point. So it is, it's not easy to see that, but it is something. So it is something that you've seen before, if you're sort of up on the homework. Anyway, that was kind of complicated, but that last one, but there it is, it works. And so if you go from the top, well, let's just go from the, we haven't done this much of this particular thing that I'm saying, but in this class, because it really is in the end building up. Even though we did a lot of review, it is in the end building up on analysis 1, but let me do this from the top. Dun, 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 dun. Suppose epsilon is greater than 0. Let delta be delta 1 of epsilon over 2 coming from part A, which means, which is really just the thing that you have in part A, except replacing epsilon 1 with epsilon over 2. And so in that case, by part A, if the distance between y and z is less than delta, then the distance between f of y and f of z will be less than epsilon over 2. Great. Okay, now assume the absolute value of x is less than delta, and now consider this the absolute value of this integral that we're trying to estimate. Well, by the triangle theorem, by the triangle inequality for integrals, you can push the absolute values inside at the cost of possibly making this bigger. And then by the green box, which really follows from the red box, you can replace this stuff, f of t plus x minus f of t, with epsilon over 2, again at the cost of possibly making everything bigger. So now we have the integral from 0 to 1 of epsilon over 2 times the absolute value of k over t dt. Well, epsilon over 2 is a constant, so you can pull it out. And k over t, well, k is already was soon be non-negative. There it is up there. And so we can replace the absolute value of k with just k, and that integral is 1. So that's right there. And so that's going to be equal to epsilon over 2, which is in fact strictly less than epsilon. Ta-da! Yeah, exactly. So it's number 8 of K. And are there any overall questions? Okay, I'm going to stop the recording right now. Where does the final circle on the bottom come from? That's a good question. So let me make a little note as to where that came from. That stuff came from. This is the red box. But with x, with t plus x, with t plus x plus x, and t instead of x and y. Yes, it's just this. Oh, and the yeah, instead of therefore, I said because. So sorry, I hope that's not too confusing. It's because instead of therefore. But so William, otherwise that makes sense. Yeah, okay. So are there any chapters that are more important? I think it's actually about 50-50. I mean, but you didn't have to ask me about that. So the way I make the exam is that I look at problem set 7 through 9, and I try to cover material on the exam in proportion to how it's covered on the problem sets. And actually, if you look at problem sets 7, 8, and 9, it's really just about 50-50, chapter 7 and chapter 8. Maybe like a little bit more chapter 8 than chapter 7, but not much more. So yeah. So it's all in the homework and everything, and everything's based on the homework. And you can really look for this one in particular. You can really look back and see like, oh, there are very specific problems that are very specific homework problems on which this is based. So yeah, it's all from the homework. Any other questions? Okay, I'm going to stop the recording. Bye, internet.